Okay, so we've talked about the importance of how we actually validate selection techniques. We're now going to talk more about how we make decisions with selection techniques. So we're going to be talking about the various practical approaches to selection, and once you have multiple selection tests that are meant to be related to performance, that you validated in some manner, how do you actually use these to make decisions? So the practical approaches to selection. Who will be likely to be successful performers? So again, that is one of the major things that we're wanting to do. The reason to do selection is to try to make better decisions. It's an attempt to make sure that we minimize the costs of bad hires while maximizing the advantage of good hires. So part of it, though, also is the battery cost effective? So when we start looking at different types of organizations and different types of jobs, one of the first questions we need to ask is how important is the job, how hard is it to find someone that is a good performer, and what is the cost of bad performance? So again, some jobs are not going to probably have the cost associated with retraining, rehiring, or the costs of poor performance to be more than just if someone poorly performs, we get rid of them and we hire someone else. In those cases, a battery of selection tests might not be cost effective. So before we move on to actually using selection techniques and selection tests or selection batteries to make selection decisions, we do need to stand back for a minute and ask, is it going to be cost effective for this job? Are we going to get payoff for using a selection system? Once we've decided that a selection system is appropriate, there's two major approaches that we can use for selection. We can use a multiple cutoff approach or a multiple regression. Both of these are based on the idea that if we're doing selection, we're using more than one test. If you're only using a single selection test, if you're just using interviews or just using cognitive ability tests, then you're just going to use that score, and you don't need a system for determining how to put together the data you get from running multiple selection tests. Multiple cutoff is a method that basically is using each test in sequence to determine who actually finally gets the offer for hire. Multiple regression is a system that uses all the tests at one time, and we're going to talk about each one in turn. So the multiple cutoff approach, it's a non-compensatory method of employee selection. What non-compensatory means is that if you are lacking in any one of the selection tests, that's enough for you not to get hired. In other words, you need to pass every test. Doing really well on 3 tests and doing poorly on 1, basically you're out of the running. Now, a compensatory method would mean that if you do really well on 3 tests and poorly on 1, you might still be rated overall highly and you still might be hired. So a multiple cutoff approach is a non-compensatory method for employee selection in which passing scores or cutoffs are set for each predictor. So if a multiple cutoff approach was being used for grad school, for instance, there would be set cutoffs on each one of the actual selection techniques used for grad school. So in this case, we have the GRE, Graduate Record Exam, which is, by the way, a test of general cognitive ability. Undergraduate GPA, which is a test of basically specific knowledge. Letters of recommendation, which includes information about personality, motivation, and a personal statement. Each one of these has a set of numbers attached to it. So GRE typically goes 300 is a pretty average score for someone applying to a master's program, and it goes obviously much higher. I think 400 is the top limit, and obviously 0 is the bottom. Undergraduate GPA goes from 0.0 to 4.0. Letters and personal statement might be rated on a 1 to 5 by the people reading them. So if we were using a multiple cutoff approach, we would select the minimum number that we would even consider before accepting the person. And you'd need to meet every one of these minimums. So GRE over 300, GPA over 3.0, letters rated at 3.5 or higher on average, and personal statement of 4.0. So if any one of those was below that number, that person would not be selected. There is cutoffs associated with every single selection. Now, just because you hit the cutoffs does not mean immediately that you get the job. Those people are then going to be looked at, everyone that made every single cutoff, and the people with the highest scores are usually going to be the ones that you'd hire. Multiple hurdle approach is just a slight twist on the idea. It's a special version of multiple cutoff, and it basically recognizes the cost and utility of each selection technique. So in this case, the predictors are actually administered in order. So like for the example that I used in the last slide, when we were just talking about the cutoff approach, someone would probably provide all of those scores at one time. Or someone might come in for a job and take a cognitive ability test, a personality test, and a work sample test, and they're all gathered at the same time. And then each one has a minimum score you have to get in order to be considered. Multiple hurdle approach uses the same idea, but now basically presents each selection tool in order, and usually each one is done from the least to the most expensive. So, for example, if you were actually looking at hiring someone where you have a personality test, it's a pen and paper online test, and you have a cognitive ability test, and it's a pen and paper online test, but it actually costs you $10 a person to have that test scored. So your personality test, you just got it offline, it's free, it's on the company website. The cognitive ability test you have to pay for, and finally you have a work sample test where a person comes in and spends an hour actually doing the job under observation. So that might cost hundreds of, if not thousands of dollars. So all of your applicants would take the personality test first, and only the people that passed the cutoff for the personality test would then be invited back to do the cognitive ability test, which costs more money. Then only the people that met the cutoff or higher on the cognitive ability test would be invited in for the work sample test. So applicants move to each hurdle after scoring above the cutoff on the previous predictor. So this is just a quick example of how this would work. So again, a multiple hurdle approach, a production line supervisor. So the first thing is given is a cognitive ability test. Only those that get the cutoff of 110 or higher on the test are allowed to continue. So from the initial applicant pool of approximately 7 or 8 people, only 3 get that cutoff of 110 or higher. Those 3 are then given a personality test. In this case, the cutoff's a 55. So again, anyone that got below a 55 does not take any additional tests. That gets us down to 2. The work samples test has a cutoff of 80. Both of them apply that had the personality cutoff and the cognitive cutoff. And again, only one person actually had the work samples cutoff. And at that point, they then go on to the interview. At this point, if they pass the interview, they're hired. It also, again, goes from least expensive to most expensive. Now, that is a multiple cutoff, often done as a multiple hurdle approach. And they're the same technique. The only difference between multiple cutoff and multiple hurdle is multiple hurdle is a type of multiple cutoff, which is also considering the cost of the selection tools. The multiple regression approach will almost always involve you giving all of the selection techniques to the same person. So they're going to get all the tests. So in this case, it's not a hurdle approach. If it was, again, that example we just looked at, they would get the personality test, the cognitive ability test, they would get the interview, they would get the work samples test. And it's a statistical test that allows us to estimate how well that series of predictors forecasts a performance criterion. So this is when we're using those validation studies that we've already conducted to actually create a prediction model based on that set of selectors. So the steps involved is you have to have a validated study. You use that validation data to generate a regression equation to predict each person's performance. Now this is a compensatory model. And what that means is that because you're looking at all the selectors at once in a statistical model, if you have very high scores in a few and one low score, those high scores might compensate for that low score, and you still might get the job. So once we actually have that regression equation, we apply that predicted scheme to applicant data to calculate scores that enable us to make a selection decision. So we basically calculate what is the overall predicted performance of each applicant, and then we hire the person with the highest predicted performance. So we rank order all those applicants based on their predicted scores, their predicted criterion or performance scores. The regression equation creates the best combination of the tests for maximizing the prediction of criterion or performance. Now, some things to consider with the multiple regression approach. We may want to also basically create a hybrid method where we set a cutoff score on the predicted criterion to exclude those below the standard of acceptable performance. So think about it this way. If you actually gave someone a cognitive ability test, a personality test, an interview, and a work sample test, and the cognitive ability test they scored almost off the chart on. They're very, very smart. And the personality test, they're the exact type of personality you want working at the company. And in the interview, they sparkled, they were charming, they got top ratings. And then the work samples test. And the job is actually a managerial job where they have to organize data and make decisions. They absolutely bomb that part of it. A multiple regression approach with no cutoffs would probably still say that person is the best person for the job. You hire them, and then you look surprised as they absolutely fail at the tasks the job involves, though everyone loves them and everyone thinks they're really smart and a great person and very personable. So a lot of times when using multiple regression, almost a safety net needs to be added of, again, combining multiple regression with multiple cutoff. What is the bare minimum skill that you're willing to accept on someone if they're great in other areas? So again, this idea of a minimum cutoff. And it combines these two methods, and a lot of organizations use this kind of an approach, where they use both multiple cutoff and multiple regression. Sometimes also you can kind of imagine situations where you would combine them in another way. So you could use multiple regression on a series of cheat predictors. So for instance, you might decide, okay, we're going to give a cognitive ability test, a personality test, and a specific knowledge test about the job. We'll give them to all applicants. We'll use a multiple regression approach to determine our top 10 applicants, but then we'll only bring those top 10 applicants in for a work samples test. And only the people that pass a minimum cutoff in the work samples test will actually be interviewed. So an example of a multiple regression approach, so in this case, all of our applicants are given all the tests, so a work sample, an assessment center, and an interview. They're ranked, and then those ranks, so let's look at Stokes, our applicant number 1. So their score on work samples was a 3, on assessment center was a 5, and on the interview criterion, in other words, a measure of how well they did in the interview, a 7. They're then added to the equation that has been created by past validation studies. So if you look again at the Stokes line on the Y predicted at the bottom there, 1.043 is the same for every single applicant. That basically is the number of what their performance would be rated at on a scale of 1 to 20 if they actually had zeros on all of their performance measures. Each number then is the actual amount that particular sample or that particular prediction selection technique adds to the prediction of performance. So again, on the Stokes line, we have 1.043 plus that 1.548 is the value that each level of a work sample score adds to performance. So we multiply that number by 3, which is the actual score Stokes got on the work sample. The next value, 0.752, is again, that's the value for each point on the assessment center that you would expect to see someone improve in their performance in the job. So again, that's multiplied for Stokes by 5 because a 5 is what they got at the assessment center. And finally, that 0.320 is the amount of explained variance that interview has in future performance. And again, we multiply it by 7. We run this equation, we add up the numbers, and we get an 11.69. That is what we would predict the performance score on a 1 to 20 that Stokes would have if we actually hired them. Notice that this regression equation, the actual numbers, the base number, the 1.043, and the actual values for each of the tests, the work samples test, 1.548, assessment centers, 0.752, and interview, 0.320, are the same for every single applicant. The only thing that changes is their scores on those 3 tests. And in this case, we find that Tomlin is the person that's rated highest, a 15.10. That's who we should hire. Now you can kind of tell, if you look at this, that if you scored really high on the work samples test and lower on the other 2, well, the work samples test has the largest number we're multiplying it by, 1.548, which means, again, that might compensate for a low assessment or interview score. So we also want to discuss, is the actual selection process useful, and we want to communicate its usefulness. So is it worth it? And when we talk about the usefulness of selection tools, we're talking about utility. How useful and cost efficient is the selection battery? And the way we usually want to demonstrate usefulness or utility is that we actually want to look at proving that it's going to save a company money. So the elements of a selection process that allow us to measure utility are first the decision accuracy. So how many people do we hire that actually do good performance once we hire them? We need to know the validity. We need to know how much of performance do we think that our selection battery is actually predicting. We need to know the base rate. What the base rate refers to is how many people are actually performing well, or what percentage of people perform well prior to the use of a selection technique or the use of an old selection technique. So if you're wanting to show that your selection technique has utility, it's worth the time and effort, you first need to know how successful was the company at hiring people prior to this new selection technique? And finally, the selection ratio. Again, how many people are actually being hired that apply? So if 100% of people are being hired that apply, that selection ratio is basically 100%. Everyone that applies is hired. The utility of a selection device in that instance would be 0, because you don't have the ability to make decisions. Now, if the selection ratio is 0.01, that means 1 out of 100 people that apply are going to be hired. That's a great selection ratio for making a good selection tool shine, making it more useful, having higher utility. So let's just kind of take a look at how decision accuracy works. So I've got an example here, and I've got a graph, and let's talk about what this graph is showing first. So on the vertical axis, up and down, is actually performance criteria. So higher scores are more performance, more success. Lower scores are lower failure. To really look at decision accuracy, we actually need to know 2 things. We need to first know what is minimum performance in an organization. In other words, what is non-fireable performance? What is performance that says you're doing your job at least adequately or better? Whatever that cutoff is, we're going to mark on this chart. And in this case, it's at the dead center. So the dead center of performance is where we're saying that is minimum performance. Now on the horizontal axis, we have the actual prediction battery scores. Again, lower scores represent someone that's being rejected. Higher scores mean someone's hired. And the second piece of information we need for decision accuracy is we need to know at what point on that prediction battery is someone hired. Now those 2 pieces of information, what is minimum performance and what is minimum scores in a prediction battery to be hired, gives us the ability to draw 2 lines through our actual decision tree. And what this is a correlation matrix that's showing the relationship between the predictor and performance. And what drawing these 2 lines gives us is it gives us 4 quadrants. It gives us first, to the top and the right, Q1. That's hits. Anyone that falls into this range is someone that we predicted would do well and actually does do well. Q3 is false alarms. Those are people that the prediction battery said would perform well, but actually once they got the job, they didn't. They underperformed. So if you take a look at just Q1 and Q3, you can kind of start to get an idea that we want to set up a system where we're getting the most people that we can into that Q1. We want to hire people that we know are doing well. Now the Q2 and Q3 on the left side of this chart are usually not actually measured, because remember, if we don't select them, we don't have performance to compare them to. So this is more theoretical, but again, most relationships when we look at correlations are fairly symmetrical, so if we know Q1 and Q3, we can do a pretty good estimate of Q4 and Q2. Q4 is misses. Those are people that if we had hired, they would have done fine, but they didn't meet the minimum score in the prediction battery, so we missed them. These were people we should have hired. And finally, Q2 is the correct rejections. These are people that we said wouldn't do a good job, and if we had hired them, most likely wouldn't. So, assuming that you're looking at a fairly strong relationship between your predictor battery and your performance measure, which this example shows, you can also adjust the cutoffs to get at different types of decision accuracy. So, for instance, if we wanted to make sure that we never had a false alarm, all we have to do is move up the actual where we predict from. So in this case, with this particular data set, we could say, well, instead of hiring half of the people and getting mainly hits, we're going to bring up the actual requirements for us to hire someone to almost the very top end of the prediction batteries. We're only going to hire people that are at a very high level on predicted success. And what's going to happen is almost all of them are going to perform. Now, the downside of this is take a look at what happened to the Q4 quadrant. We are not hiring a lot of people that would have done very well in this job. Generally speaking, companies are only going to do this if the cost of failure is catastrophic. So NASA is a very good example of this. Thousands of people apply to be astronauts, and most of them are very qualified. They are incredibly smart, they're driven, they have high educations, they're usually very successful pilots, and they go through months of selection techniques before they're finally actually hired to become an astronaut. Most of the people that are rejected from NASA probably would have been excellent astronauts, But the cost of a poor astronaut, the cost of someone that makes a bad decision when the craft you're piloting costs $500 million is so high that NASA wants to make sure that only the truly best people end up actually being astronauts. So they're willing to move that selection cutoff all the way to the top to make sure they get no false alarms. No one that they think will do a good job that ends up not doing a good job. Now again, we can move it the other direction. So if we want to make sure that we don't miss anyone, we can move that selection battery all the way down. And a lot of times companies that have to hire lots of people with maybe a small applicant pool are resulting to have to make these decisions. They basically decide, we're still going to be able to get rid of some people. So we're going to cut off that Q2. We're missing no one now. Anyone that has the potential to do well in this job, we're hiring. We're also getting a fair amount of false alarms, but we're also getting a solid number of correct rejections. So if we were using no selection, we would be getting all the hits and all the misses. We would be getting the correct rejections, we'd be getting the hits. In other words, basically half the people we hired would do well, half the people we hired would do poorly. We're still getting Vegas odds here. We're still stacking the deck to our advantage. We are getting all the hits, we're getting some false alarms, but we also are successfully getting rid of at least some of those poor performers, the Q2 section. So decision accuracy is simply the percentage of hiring decisions that are correct. It's usually calculated by looking at the number of people that you actually hire that are successful divided by the total number of people you hire. So basically Q1 divided by Q1 and 3. So if you hired 50 people and 30 of them succeeded and 20 of them failed, your decision accuracy would be 30 divided by 50. Overall decision accuracy is Q1 and Q2, the correct rejections and the correct successful hits. So basically Q hits and rejections divided again by the total. And a lot of times we won't have access to this number. The only way you can get this number accurately is if you give a selection technique to everyone and then hire everyone and track all of their performance. So the goal of a selection battery is to maximize hits, Q1 and Q2, hits and correct rejections, and to minimize the misses and the false alarms. So we want as many of our participants to be in quadrant Q1 and Q2, and as few of them in quadrant Q3 and Q4 as possible. And that's why validity is important. The stronger and more valid a test is, the more that test or that selection battery is related to performance, the tighter that cluster of data is going to become. So when the previous slides, when I had those big pink blobs up there, those pink blobs were basically representing individual people's scores and kind of how they varied across prediction and actual performance. So maximizing hits and correct rejections while minimizing misses and false alarms will occur to the extent that the selection battery is valid. The more valid it is, the more people are going to fall into that hits and correct rejections category, and the less people are going to fall in that minimizing misses and the false alarms category. A selection battery with zero validity is equivalent to random hiring. It has no validity. So let's take a look at this again. So we're back to our graphs. This time, I've got an example, my big pink blob in this case, which is basically just visually representing the cluster of each individual person's score on their prediction battery score by their criterion or performance batteries or performance score. And this represents zero correlation between the two. That really doesn't give us anything. And you can tell we get an equal number of hits, misses, correct rejections, false alarms. This is a selection battery that is giving us no information other than just what we'd get for randomly hiring people. But if we have a highly valid selection, in other words, the prediction battery is very related to performance, explains a lot of performance. Notice what happens now. Now we're looking at almost all of our participants are either in the Q1 or Q2 mark area. And also, if we wanted to make sure we only got hits, we would only have to nudge the prediction battery cutoff over a few points to get rid of those small number of false alarms. Now again, by doing this, we would increase our number of misses a bit, but it's a lot easier to make good decisions with a solid and strong, valid predicting battery. Now here's what we probably have more of, a okay predictor of performance. So in this case, again, the hits and the correct rejections are larger than the misses and false alarms, but most of the decisions we make are going to include some false alarms and some misses. but it's still going to be better than if we didn't have the selection technique at all. And again, back to what happens when we have no validity. At that case, we actually have no prediction. The hits, the misses, the correct rejections, the false alarms are all equal amounts. So that is decision accuracy. So all the slides we've been talking about is different ways to conceptualize, visualize, and think about how accurate is our decisions. And generally, the way we're going to actually quantify decision accuracy is simply the validity of the test. What is the correlation coefficient, the R, if you will, of the predictor battery with actual performance? The next thing we need is base rate. So the percentage of current employees who are successful on their job with either no selection techniques or an old selection technique that we're arguing needs to be replaced. It reflects the quality of previous selection batteries and provides a basis of comparison for a new selection battery. Organizations generally set cutoffs based on a criterion. So basically, the criterion is performance. Again, what is minimum performance? What is the number of people in the organization currently that are making that minimum of performance? The selection ratio is the number of job openings divided by the number of applicants. If you have 10 openings and 10 applicants, 10 divided by 10 is 1. That's basically a selection ratio of 1.0. You are hiring 100% of the people that apply. If you have 10 openings and 100 applicants, 10 divided by 100 is 0.10, or 10%. You're only hiring 10% of the people that you are applying. The smaller the selection ratio, the smaller that percentage, the greater potential for the utility of a selection battery. So this emphasizes the importance of recruitment for increasing the number of applicants, especially qualified applicants, so organizations have more options to allow selection techniques to work. We do also need to consider cost. So organizations are driven by bottom line, so selection battery cost is a strong consideration. If costs are so high that they're greater than the potential increase in revenue from hiring good employees, or are so high that it would be cheaper just to be making the mistake, then the new selection battery is less desirable. Again, when I was talking about NASA and the techniques it uses to select, it's comparing what is the cost of failure, what is the cost of hiring a poor astronaut. And that cost is very, very high, and therefore they're willing to spend a large amount of money to do a very complex set of selection techniques to get the very best astronauts. So, if we want to estimate utility, there's 3 pieces of information we really need that we're going to focus on. We need the validity of the selection battery, we need the organization's base rate information, and we need the selection ratio. And a lot of tables have actually been created to give you quick and easy ways to estimate how successful a new selection technique is going to be. Taylor and Russell has a whole series of tables, and I've got an example we're going to look at next to kind of illustrate how this all works. So, here we have a Taylor and Russell table. Now notice that the first thing we have at the far left is base rate information. Now, a lot of these tables will have base rate information at every level. 10%, 15%, 20%, 30%, 35%. This table just has a few examples. So we're going to just look at 30%. So we're looking at a base rate of 30%. What that means is for every 10 people this company is hiring, only 3 of them are performing adequately. So they've got a pretty bad base rate right now. Now, currently, what they're doing to hire is nothing. They have no selection technique, so the validity coefficient is 0. They're basically just flipping a coin to see if they hire people or not. Now, their selection ratio, though, is pretty good. For every 10 people that apply, only 2 are being hired. So they have a selection ratio of 0.20. 20% of the people apply are being hired. Now, with a validity coefficient of 0 at a base rate of 30, hiring 2 out of 10 people, our selection ratio is still going to be 0.30. In other words, with this current system, it doesn't matter what the selection ratio is, because we have no validity and we're just flipping a coin effectively. We're just choosing it on non-work relevant conditions of who we hire. Then, of those people that we hire, we expect only about 30% to perform well. Now, what happens, though, is if we change those numbers. So we're still at a base rate of 30%. That's the past base rate. But now, and we still have the same selection ratio. Every time we post a job, for every 10 people that apply, we get to hire 2 of them. But now we add a new selection technique that has a validity coefficient of 0.50. That's explaining about 25% of performance. Notice what happens to the new selection ratio. Using this selection ratio, we can estimate that given the selection ratio and the base rate, we're going to move from 30% success to 58% success. Now, that still indicates that 42% of the people we hire are still going to be below the line, but we've just moved from where 1 in 3 people are performing to where over 50% of the people are performing at accepted levels. This illustrates utility.